So we've seen the conceptual approach to enable out-of-order execution while retaining precise state so that we can handle exceptions and control misspeculations in this out-of-order pipeline. We can retain correct sequential semantics. We saw that the reorder buffer, at least abstractly, implements that concept of the instruction buffer or instruction window. And we've broken the decode and write back stage into two parts. We dispatch into the instruction window in order, issue to execute out of order, complete instructions out of order, buffering their written results, and finally retire instructions in order so that we can always abort and restart at any given instruction because the precise state of the architecture is available to us in these various hardware data structures. In this video, we are going to see one particular implementation, the MIPS R10K, of this whole pipeline design. And as I alluded to earlier, a key supporting data structure is the notion of a physical register file to provide more locations than names, in contrast to copies in the reservation stations that we saw in Tomasulo's algorithm. But with the move to a physical register file, we have some new concerns arise, which I'll remind you through a register renaming example, harkening back to the first way that we encountered register renaming early in the module and dynamic scheduling. So in this example, our ISA defines 3 register names, R1, R2, and R3, but we, the computer architects, we control the hardware, so we can actually provide more locations than there are names, and we'll call them physical registers, P1 through P7. Register renaming relies on a map table to map each name to the location holding the last write to every register name. So in this example, the original mapping is R1 to P1, R2 to P2, R3 to P3, while the rest of the physical registers, P4 to 7, are free. They're available to be allocated. We dispatch the first instruction, the add. We look up in the map table to find out that R2 and R3 are renamed to P2 and P3 respectively. And since the instruction writes R1, we must allocate a new physical register and update the map table accordingly. So arbitrarily, we pick P4 from this free list of allocatable physical registers and update the map table. And the subtract instruction, it finds the mapping of its read registers, and so on the process goes. But we have a problem that I told you that we would return to back in the last module, which is how would we rename the instruction after the divide? We're in trouble. We dispatched and allocated for 4 instructions, so now we have an empty free list. We are out of available free locations, physical registers in the design that we're about to see. This is a question we will have to grapple with in the MIPS R10K design. In particular, we need to ask how and when should physical registers be freed? So from that abstract introduction, we move to the concrete. How does register renaming work in the R10K implementation? What happens to the architectural register file that we saw in Tomasulo in the 5-stage in-order pipeline? It's gone. The notion of architectural registers is that they are names only now. Instead, it's the physical register file that holds all values. So the number of physical registers exceeds the number of architectural registers. Those registers named in the ISA. Now, how do we possibly find the right data for a given register named by an instruction? Well, of course, we map the architectural register names to physical registers. So through this mapping or renaming, this is how the MIPS R10K design removes write after read and write after write hazards. In this design, we replace the reservation station copies from Tomasulo's algorithm with locations in the physical register file. Now, such a design results in a fundamental change to the map table. In particular, the mappings in the map table can no longer be null, cannot be 0, cannot be empty, because there is not an architectural register file anymore. Recall that with Tomasulo, an empty tag in the map table indicates that the value in the architectural register file is up to date. It represents the last write to that register name. But we're opting for a design where the collection of physical registers contain both the old and the new values for register names so that we can recover to a particular state when necessary. So in this design with a physical register file, we need a free list to keep track of the unallocated physical registers. Returning to that question I had before, how and when do we return a physical register to the free list? Well, the reorder buffer, which for every instruction holds the new and old tag for its output register so that we have the data available, the old tags, to recover precise state. Well, the reorder buffer is responsible for returning registers to the free list. This happens at the retire stage, where an instruction is no longer speculative and won't be interrupted. Conceptually, this physical register file-based approach is true register renaming in contrast to the copy-based approach that we saw in Tomasulo. Okay, let's dive into the implementation, the design of the MIPS R10K, starting with the organization of the microarchitecture, followed by a description of the key data structures and the operations performed in each stage of this pipeline. So instructions are still dispatched in order, at which point they allocate entries in several structures, including reservation stations, but we also need an entry in the reorder buffer, and we'll have to request a physical register from the free list at dispatch. Dispatch still looks up the tag of each input operand register name in a map table, but the definition of the tags has changed somewhat, now pointing to physical registers, which I'll reiterate again. The major change in this design is that now one big physical register file holds all of the data, and there are no copies in the reservation stations. So this is the physical register file containing all of the locations we will use for register renaming. Say physical registers 1 through 7 in that example above, or maybe 1 through 128. It depends on how one allocates resources on chip. So now that all values are held in the physical register file, notice there are no values in the reservation stations, only tags for the input registers and the output register. You can see that the ROB holds the new and the old tag for the output register of every instruction in order. It's a FIFO structure. And I'll note that a key feature of this design is that the register file, the physical register file, is now very close to the functional units, and this enables a small, fast data path. In the Tomasulo design, in the copy-based reservation station design, we had more wide wires to move data around the various structures, but now we can put those wide data paths closer together between the actual functional units and the physical register file. So notably, the reorder buffer and the reservation stations are off on the side. They're only used for control and tags, enabling shorter wires. And one last note, in this organization, we still have a common data bus, but it's only broadcasting the tag of a completed instruction now, as the values are sent straight to the physical register files. Okay, let's see how all of these components interact together. So let's get into the data structures of the R10K. So this design has new tags. Tags still map a register name to its physical location, but whereas in Tomasulo, a tag represented the reservation station ID of an instruction that would produce some given register name, or 0, if the value was in the architectural register file. Now, instead, in the R10K design, the tags hold the physical register number in the physical register file. The reorder buffer holds the new and the old tag for a given instruction. So that's the physical register corresponding to this instruction. So the ROB entry instruction's logical output is register name. It's output register name. And the second field in each entry of the ROB is the old tag. So it's holding the physical register ID previously mapped to this instruction's logical output. This is the state that enables recovery, that enables precise state. Reservation stations still exist, but in a modified form, containing only tags. So T, S1, S2 in the previous diagram hold the output and input physical register numbers for the reservation station entries given instruction. You may have noticed a plus symbol beside those tags, and this is one additional bit in the tag. So it's a tag plus that indicates whether the data in that physical register is actually ready to be consumed. The map table is again indexed by register name and holds a tag plus. Same idea, the latest physical register number for that name, which can never be empty or null anymore. Every architectural register must be mapped to some physical register, plus a ready bit. Has the instruction that allocated this physical register actually finished execution and completed the result? In the free list, we have a set of tags holding the physical register numbers. These physical registers, of course, shouldn't have any notion of a ready bit. They have been deallocated. They're not participating in any active instruction in the instruction window. And a final reminder that there are no values anymore, no register values in the reorder buffer, in the reservation station entries, or even on the CDB. when an instruction completes its execution, the value is sent straight to the output physical register of that instruction. There are other designs of out-of-order execution with precise state that do embed values into the reservation stations or reorder buffer. This is covered in chapter 3.4 of the textbook, but I won't cover it in lecture here. Okay, so we've seen the organization of the R10K and the definition of the data structures. So naturally, let's move to that algorithm, to the R10K pipeline. What is happening in all of the stages? Well, notably, fetch and execute don't really change. Here we'll focus for the most part on dispatch and issue, and completion and retiring. Let's start with the dispatch stage. What do we need? At the very least, we need storage for all kinds of structures. So first, we have to check, are there any structural hazards? Is there space available in the reservation station for this type of instruction, in the reorder buffer? And can we get a physical register for the output? Is the free list non-empty? If we have a structural hazard on any of those structures, then of course we stall, which propagates to younger instructions in the fetch stage. If not, we move on and we allocate a reservation station entry and a ROB entry, a new physical register, and we update the map table with the tag of that new physical register for the output register name. We also read the physical register tags for the input registers and store those in the reservation station fields. So that's the S1 and the S2 fields in the organization shown above. To collect the state required for recovery, we also read the old physical register tag for the output register name and store that in the ROB, the told field. And finally, we store the new output tag, T, into the fields in the reservation station and ROB. Okay, our bookkeeping is set in the dispatch stage. So moving on to execute. Well, it's between issue and execute. This is the first cycle of execute right after we've issued. What do we do here? We free the reservation station entry. And this is new, this is exciting. It used to be that we held on to the reservation station entry until writeback, but now it can be earlier, specifically because the reservation station entry is not the tag. So we're no longer using the reservation station for our register locations, so we can free these entries a little earlier now, putting less demand on the structures, reducing the risk of structural hazards, at least on the reservation station entries. Moving onward into the pipeline, we come to complete. So this is the cycle right after the functional unit has latched its output, say a long latency floating point operation, or we finally have received data from the cache and we've latched it. So in the next cycle, the instruction enters the complete stage. It writes the destination, the output physical register directly in the physical register file. That's the large loop here from the functional units to the value to the physical register file. But as the old saying goes, if a physical register is written, but no one is around to hear it, did we really produce a value? Of course not. We need to tell all of the instructions that want this value that the data is now ready. So through a broadcast on the CDB, only broadcasting the tag, we set the instruction output register ready bit in the map table, so that later readers of that register name will know the operand is ready and maybe can issue if both operands are ready. And for those instructions patiently waiting in the reservation station, again, through a CDB broadcast and tag match, we set the ready bits for the matching input tags, that's S1 and S2, in the reservation stations. So when both S1 and S2 have their ready bits set in the reservation station, they can then be issued to the functional units. And last but not least, the retirement stage is responsible to ensure we don't run out of storage space. We're keeping old and new copies of these tags so that we can recover state, but we need a way to deallocate these safely, and so we free storage in program order. To help me explain this stage, I'm going to refer back to the diagram again, just briefly. So we've seen now that the ROB is a FIFO queue, one entry per instruction in the instruction window, and it holds two pointers to represent the start and end of the current instruction window. The head pointer indicates the oldest active instruction, so it's in the functional units it's executing right now, and the tail pointer indicates the latest instruction to have been dispatched and where it is in the ROB. So the goal of retirement is to move that head pointer downward so that we can allocate more ROB entries to future instructions. So what are the actions of the retire stage? Well, we check, is the ROB head instruction not complete? If that head instruction is still executing, then we simply stall. We can't deallocate any entry in the ROB. But otherwise, if that head instruction has completed its execution, then at retirement stage, we handle any exceptions. So yes, at last, we have a means to enable precise exceptions. If there weren't any exceptions, and if the instruction was a store, then finally we can write the value in the data field from the load store queue that I mentioned in the last video into the data cache / memory to ensure we have precise state not only in registers but also in memory. And now that we know that this head instruction is no longer speculative, its control path is certain, it didn't have any exception, then we can free the reorder buffer entry and the load store queue entry if relevant. We don't have to keep a backup of the old output tag, and we can give back the space so we can free the previous physical register, the physical register pointed to by the told field. And that's it. We have covered the design of the MIPS R10K approach to dynamic scheduling with support for speculation and exceptions. We've achieved precise state. In the next video, I'm going to cover an example of how all of these parts interact together to make this more concrete, just as I hope the examples for Tomasulo helped to elucidate some of those concepts. So I'll see you there.